You know that feeling when you're staring at a spreadsheet, just a sea of numbers, and it all feels like, well, just random noise. What if I told you there's a way to find the hidden story in there, to pull a clear signal out of all that chaos? Well, there is. It's called simple linear regression, and today we're going to break down exactly how it works.
Okay, so here's our game plan. First up, we're going to tap into something we all do naturally, spotting patterns. Then we'll take that intuition and turn it into a perfect mathematical line. After that, we'll get real and figure out how to handle the messy data of the actual world. We'll uncover the secret to finding the one single best line, and then, to wrap it all up, we'll see how this connects to the high-stakes world of financial markets. Sound good? Let's dive in.
All right, first up, so imagine you're a data scientist, or hey, even just a curious person. Somebody hands you a data set, and it just looks like a cloud of points on a graph. Where do you even begin to find any meaning in that? That's the first big challenge we're going to tackle. I mean, this is the fundamental question, right? Let's say we're looking at something like, I don't know, the amount of sugar in different cereals versus how much people rate them. Is there a real connection there? Does more sugar actually lead to a higher rating? How can we possibly know for sure? So the amazing thing is, our brains are basically hardwired to be pattern finders. Just look at this scatter plot. I bet, even without thinking about the math, your brain is already trying to draw a line that kind of slopes upwards, right through the middle of all those dots. Well, that instinct you're feeling right now, that is the core idea that regression analysis formalizes into a super powerful tool. Okay, so we've got this intuitive idea of a line, but intuition can be a little fuzzy. To make this a real solid tool, we need to go from just a gut feeling to an actual formula. So let's start by building the perfect, idealized version of this line. So in a perfect world, right, our data would be super simple. This equation here, this is what's called a deterministic model. The best way to think about it is like a perfect recipe. You put in an exact amount of ingredient X, and you get an exact result Y. Every single time. No surprises, no wiggle room. And you know what's cool? Every single straight line in the universe is defined by just two numbers. First, you've got beta 0. That's the intercept. It's basically our starting point. What's the value of y when x is 0? Simple. Then you have beta 1, the slope. And this is where the action is. It tells us how steep the line is. For every single unit you move to the right on the x-axis, how much does the line go up or down? That's the slope. But that perfect recipe, that's not how the real world works, is it? The real world is messy. It's unpredictable. So now it's time to leave that clean, perfect world of theory and figure out how to make our model actually work with real chaotic data. And that brings us to a huge problem. That perfect line is great, but look at our actual data. The points are scattered all over the place. They don't follow our neat little equation. So what do we do with all that mess? Just pretend it isn't there? Yeah, this image shows it perfectly. See that straight line? That's the ideal, true relationship we're hoping to find. But then look at the actual blue dots. That's our real data. They're all scattered around the line. And that distance, that little vertical gap from each dot down to the line, that's what statisticians call error. It's basically the randomness of the real world messing with our perfect model. And this is where our model gets a huge upgrade. We add a new character to our equation, this little Greek letter, epsilon. You can think of epsilon as kind of like the randomness factor. It stands for everything we can't possibly measure, pure luck, tiny measurement mistakes, all the chaos of reality. By adding epsilon, our simple line suddenly becomes this powerful tool that actually embraces uncertainty. We've just gone from a perfect but useless model to a realistic one. Okay, great. So now we have a model that can handle some randomness. But think about it. With a cloud of data points, you could draw like a million different lines through it. An infinite number, really. So how in the world do we find the one single line that is truly the best fit for our data? Well, the solution is just this beautifully elegant idea from the legendary mathematician Carl Friedrich Gauss. It's called the principle of least squares. And what it says is that the best line isn't just one that looks good to our eye. No, it's the one that makes the sum of all those squared errors as tiny as it can possibly be. It's a mathematical way to find the absolute minimum amount of total error. And this graph gives us a perfect picture of what least squares is actually doing. Each one of those vertical lines represents the error for a single data point.
So the least squares method is kind of like a mathematical game of limbo. It's trying out all these different lines and finding the one single line that can duck down and get the total of all those squared errors as low as it can possibly go. And that one, that's our line of best fit. So we found our best possible line. Awesome. But, best can be a relative term. How do we actually measure how good this best fit line really is? Like, is it a genuinely good model for our data? Is it actually useful for making predictions?
To do that, we need a number called variance. And you can basically think of variance as a quality score for our line. If the variance is low, it means our data points are all huddled really tightly around the line. That's a great fit. We can be pretty confident in our model. But if the variance is high, it means the points are scattered all over the place. Our line might still be the best one possible, but it's not a very good predictor of anything. And this is a really fantastic way to visualize what variance actually means. At any point along our line, you can imagine the data points around it forming a little bell curve. Now, if the variance is low, those bell curves are going to be tall and skinny, which means most of the data is packed in super close to the line. But if the variance is high, those curves get short and wide, showing that there's a whole lot more scatter. Okay, so we've been pretty deep in the weeds with the statistics, but now let's pull the camera back and see why mastering this seemingly simple idea, just drawing a line through some data, has such massive implications out in the real world. It's really easy to hear the word simple and think unimportant, but do not be fooled. This method is the absolute foundation. It's like the alphabet of modern data science and even machine learning. I guarantee you, almost every complex model you've ever heard of has a little bit of simple linear regression buried deep in its DNA. And here's a perfect example of just how far these ideas can take you. This is the Economics of Financial Markets. It's a landmark book that takes the exact principles of regression we've been talking about and applies them to one of the most complex systems on the planet, the global financial market. See, inside this book, the authors take the basic tools we've just gone over, finding a line, measuring the error, and they use them to tackle some of the absolute biggest questions in finance. I'm talking about things like, can we actually predict stock returns? Is there a hidden order inside all the chaos of the market? All of these huge, massive questions, they all start with the principles of regression. And the result? Well, this book isn't just some dusty academic exercise. It's considered a modern classic that literally builds upon and enhances Nobel Prize-winning work. It just goes to show you how incredibly far you can go when you really master the fundamentals. And to think, it all started with just drawing a line through some dots. It really makes you wonder, doesn't it? What other complex patterns, maybe in your own world, or your work, or even just in the news you read, are just sitting there waiting to be unraveled? All it might take is starting with one simple line.